there's a holy grail of the cosmologists, which is what they call it used to be called the Copernican principle, but it's now called the cosmological principle, which is...
The cosmological principle is the assumption that the universe is homogeneous and isotropic. That is, on the big scale, it looks the same in all directions, has the same properties everywhere.
If the universe is isotropic, with one exception that I'll describe in a moment, if it's isotropic around us, then you can bet with a high degree of confidence that it's also pretty close to being homogeneous.
Therefore, homogeneity and isotropy are not the same thing, and they don't imply each other. One is where we stand, and the other is where we look.
So therefore, we should see that but now we have two definitions, isotropy and homogeneity.
And those are assumptions. They're not provable. They seem reasonable. They seem plausible. And much of 20th, now 21st century cosmology are predicated upon that.
Even with all this, it is sufficiently uniform on cosmological size scales to justify using a metric that assumes perfect homogeneity and isotropy. That assumes perfect homogeneity.
Now, of course, if you look right at a star, it looks a little different than if you look at away from the star.
Of course, all the matter and energy in the universe is much too complicated to put into the equations and have any hope of solving them. But if you zoom out enough, you can approximate the universe as having a roughly constant density everywhere and in every direction.
He found, surprisingly and unhappily, that the universe could not maintain a fixed size. He found in his mathematics that the universe would either be expanding or contracting.
And Einstein was able to solve the equations for a very simplified universe with constant density everywhere.
Unfortunate from his perspective that this math that he had developed for over a decade was incompatible with this basic fact of the static universe.
Science is failing. It's failing right in front of our eyes.
Fails in its attempt to predict the amount of dark energy in the universe.
Yeah.
And it fails badly by a factor of a Google.
Wow, by a factor of bigger than a Google. It's like 10 to 123.
You can just add on a very simple term without violating any key principles of physics.
Science is failing.
You can approximate the universe as having a roughly constant density everywhere.
Is failing.
You can just add on a very simple term.
Is failing.
Badly.
So what is going on here? Why do cosmologists seem so confused all of the time? The universe is expanding because the cosmological principle and the cosmological constant tell general relativity that the universe is not collapsing and that it needs to use the dark magic energy to change the co-moving coordinates and the homogeneous mass density over time. You know, none of these concepts, dark energy, dark matter, expanding space, cosmological constant, these are not concepts from general relativity. Relativity is a theory about relationships. It's not a theory about space-time curvature. It's not a theory about the energy content of the vacuum. It's a theory about the laws of physics. So there are several core principles and postulates within general relativity. But the principle of general covariance is the one responsible for all of the heavy lifting. The principle of general covariance essentially says that the laws of physics must take the same mathematical form in all coordinate systems. So if you have an equation, a physical equation, it has to be the same physical equation regardless of whatever arbitrary coordinate system you have chosen. There are several implications that follow this, but perhaps the most important one is that Maxwell's equations imply that the speed of light is a constant for all observers. And so this constancy of the speed of light may seem benign at first, but it has dramatic consequences after you've thought about it for a little bit. The bowling ball on a trampoline example is obnoxiously inaccurate. It's a representation of nothingness. I mean, it's just nothing. Their mass does not curve space-time. This is a misnomer. Mass, the presence of mass causes the relationships between other mass and energy to change. You can say that space contracts and time dilates. But curvature, the word curvature refers to two different things. There's the curvature as in a reference to the shape that gravity produces, as in planets and stars. This is a sphere, and so it's curved. But that type of curvature only occurs because there's a symmetrical nature in the way that gravity manifests. The other type of curvature is a reference to the non-linear nature of relativity, or general relativity. Like the Lorentz factor, or the Z factor in general relativity. This phenomenon, it's an exponential or a hyperbolic curve. It's not linear. Mass is also not attracted to other mass because it curves some underlying space-time substance, like a trampoline. Instead, what we call gravity comes from the relationships between the systems of mass and energy. And that's it. General relativity describes how any given system, any chosen coordinate system, any chunks of mass, how it evolves in relationship to the rest of the universe. And it does this through the metric tensor, which is determined by the stress energy tensor. You don't even need space-time, not in a physical sense. You just need a numbering system to be able to keep track of all of the relationships. It would be difficult to do it, but you could. It's entirely possible to formulate general relativity without using space-time at all. In fact, there's all kinds of theories out there in quantum gravity and quantum field theory that try to do that exact thing. They are trying to show that space-time is an emergent property. But I would like to suggest that the last thing we need is a brand new theory. Honestly, general relativity is all we need to solve all major problems in physics. I know that sounds outrageous to hear. There's so many crackpots in the world, but it's true. When I began my research in circa 2009, I was laser focused on gravitational redshift. That's because early on, I found a super simple way to align gravitational redshift with the Hubble redshift. And there was essentially no information about it on the internet or anywhere. Zwicky, that was like one of the articles I remember early on finding and being like, no, this is not, it's kind of close. Like, at least he tried. But, there's pretty much nothing on it. Even today, there's nothing. There is a lot of discussion, a lot more discussion these days, talking about cosmologies, the anomalies in lambda cosmology. It seems like there's a lot more criticism, that it's way more acceptable these days to question. It's more acceptable in the modern era to question mainstream physical ideas. And all throughout the 2000s, if I asked a question on a physics forum or on Reddit, I would get banned. Like, no joke. I got banned from Reddit cosmology numerous times, and I would always try to frame it in a question, and they would just ban me. Same thing with like Ask a Physicist or anything like that. I despise forums. I despise it. I've been banned from all of the major forums. Anyways, let's get back. I want to introduce my cosmological model to you. Now, if you are subscribed here, you know you've heard this before. Although there may be some different things, I'm constantly updating it and refining it. I'm not a professional, and I'm always making little small errors, but the gist of it has remained the exact same. So it's literally refining and improving. I'm not changing or backpedaling. I haven't done any of that. Most of my work has been on trying to figure out a way to communicate the ideas. The math behind it's pretty simple. The physics is pretty simple. Let's get into it. So these days I've been placing all of the proposals into a single basket, which I refer to as the relational properties of mass. Basically, what I'm doing is demoting space-time as a physical substance. It's no longer an ontologically real thing. It's an abstract, human-created concept. It's a property of mass and energy. Now that's kind of abstract and hard to wrap your mind around, but essentially my proposal is that we interpret the gravitational the cosmological redshift as gravitational redshift. Why? Because space-time can't expand. It doesn't have properties of its own. So space-time is not something that changes with time. And so you can't have an expanding universe that way. I mean, you can maybe have an expanding universe if there's a giant explosion that makes things expand. But, you gotta have something. Like you can't just say space-time expands. So you have to use general relativity to explain the cosmological redshift. If we can't use expansion, you have to use mass and energy. And you can do this. This is easy. On the right-hand side of the screen in the center is my mass density profile. And so I've stated this as rho of r is proportional to k over r, and that's correct. That's a fine way to say it. You could say that it's proportional to 1 over r. I mean, it's not actually 1 over r. It's 0.833 kilograms per meter squared. And it's actually not k over r either. It's 3k over 2r. Now, what does that mean? It means the universe is not homogeneous, that mass density is a scale-dependent variable. It depends on how much of r you're talking about. There is no 0 point. I could normalize this, and I guess I probably should for all the nitpicky people out there, but you don't have to have r equals 0. You can have r equals 1 Planck length, or 1 megaparsec, or whatever minimum length you want to use. For this, it does range on the local scales, but all of the local drama gets drowned out on the cosmological scales. So on the left-hand side, there's the mass equation is the top left. The m of r equals 2 pi k r squared. Now, I don't have it here, and don't know if I've already said it, but k equals 0.833 kilograms per meter squared. That's what you need to have to fit for Hubble's law. And so the equation below that in the center left is the Hubble constant. That's the 4 pi g k divided by c. Excuse me. We can, you can divide that by r to get the standard, Hubble's law. If you want 72 kilometers per second per megaparsec or whatever. But this equation will equal 2.33 times 10 to the negative 18 seconds, inverse seconds. And below that is the Z. This is the gravitational redshift. This is what the Hubble's law will do. Now, there's a radius or a horizon. At the top, the very top center equation is our horizon. RH equals c squared divided by 4 pi gk. And so you get 1.28 or 1.277 times 10 to the positive 26 meters. So it's around 13 billion light years, something like that. That's for my K equals 0.833 kilograms per meter squared. Now we can adjust the K based on whatever Hubble measurement you want to use. But for this, I used 72 kilometers per second per megaparsec. And I think that's probably the right figure, because the CMB, temperature equation, which is on the bottom right. Why am I doing the uptalk thing, which is on the bottom right? Sorry. It's just you turn the microphone on and your brain goes to mush. But this is the CMB temperature equation. If you're familiar with this equation, this is the Hawking temperature equation. And I reinterpret the cosmic microwave background radiation as blue shifted Hawking radiation. And my reasoning behind that is that we have a Schwarzschild radius. And so it seems to me like we should have Hawking radiation. Look, there's many different metrics you can formulate this with. I mean, not really, but there's many ways of expressing this with general relativity. But you know, any solution to the field equations that you come up with is it should, because of Birkhoff's theorem, it should resemble the Schwarzschild metric in the end. And my argument for that is that symmetry is another product of scale. The larger the scale, the more symmetrical the universe. And that seems to me like good enough logic to bring Birkhoff's theorem in, especially for the very large scales. Yeah, sure, the first few hundred megaparsecs may vary, but you know, as you get to that Z equals 2 threshold, I mean, the universe is very symmetrical at that scale. And so I see no reason why you shouldn't use spherical symmetry and use the Schwarzschild metric. So we have a horizon. This is an observer-dependent horizon. So in other words, we're looking at a star. We're looking at a star that's embedded in the center of the universe. All stars are embedded in the center of the universe. All observers are embedded in the center of the universe. That's because there is a horizon. It's a little abstract, a little crazy, but if you just think about it for a moment, you have a distance proportional redshift, and so there's going to be a horizon regardless of whether it's caused by gravitational redshift or the expanding meter. Hopefully this graphic brings that into, into perspective a little bit. Another one of the things that comes out of this relational properties of matter, in other words, there is no space-time. There is no physical space-time, I think, is the best way to say it. One of the things that comes out of that is that there are no gravitational boundaries. And this is something I've been saying for a long time, for well over a decade now. I've been saying it publicly, and people like mainstream physicists have to agree with this, but they don't know what it means. And I wish that they would just contemplate on it for a little bit longer. There are no such thing as gravitational boundaries. What we call the sun is the sun because it's there and it seems obvious. But the sun is actually surrounded by mass. There is no place in the universe where there's no mass. The vacuum is not real. The vacuum is an idealized concept. It's the absence of mass. Well, we live in the universe. There is no such thing as the absence of mass. We have less mass and more mass. That's it. There is no absence of mass. Which means there are no gravitational boundaries. Hey, even if you create a vacuum artificially, you did not create gravitational boundaries. The vacuum is still full of quantum fields emanating from mass energy and radiation. These are unavoidable. You cannot get rid of them. And so there is no such thing as a boundary. This is a human thing, like it's useful. I'm not saying that these concepts aren't useful. It's definitely useful to have something called the sun. But it's not like there's a book of stars out there on God's desk and each star has a X properties. In reality, they're all part of the same big object. There is no distinction between them except for the arbitrary human boundaries that we give them. Of course, if you're talking about singularities, there are certain properties to an object, like Hawking radiation, and this is a singularity. It's a coordinate singularity that comes from the chosen coordinate system, but it's a singularity nonetheless. It's a mathematical artifact. Okay, that's the best way to describe it. It's an upper limit to the relationships that mass and energy have in general relativity. Hear that whippoorwill? Whatever. He stopped immediately as soon as I mentioned him. Anyways, I've attempted to represent this horizon here with this graphic. On the left side, you have the observer. And so, if there's like the sun is closer to the earth, so there's less gravitational redshift in the sun. Now it has gravitational redshift because the sun is a massive object. And so the light, as it immediately leaves the sun, it has to travel uphill. And so it's traveling uphill. It never stops traveling uphill. It leaves the galaxy. It leaves the cluster. It leaves the rest of the universe. Like, that's what it's doing. It's accumulating gravitational potential as it's traveling. Now, you can have an observer like at the edge of a black hole and it counteract this. Or you can have the observer, like say with certain radiation, as in this Hawking radiation that I'm suggesting, it's blue shifted. And now the observer is in the center of the metric. And this is just, I have to reference Birkhoff's theorem because this is the general idea. The general idea is that we treat starlight with null geodesics. You really don't even have to formulate a metric for the universe. If you want to, that's fine. That's fine. But I don't think that it's representative of much of anything. General relativity is all about, it's all about context. It's the relationships between one coordinate systems and another. and the coordinate system is chosen by you. And so it's very, very contextual. And you can formulate the universe as a metric solution if you'd like, but that it's not indicative of how the universe will evolve in the future. That's not to say that this universe is unstable. You can totally create a stable universe with this. The Jeans argument, I mean, there's a boundary here. So Jeans argument doesn't apply outside the boundary. And also, perturbations are scale dependent. You can't just throw in an enormous perturbation and expect the universe to be stable, but I bet this one would be stable. I bet it would just create an enormous black hole, and there is going to be another black hole somewhere else in the universe to kind of balance it out. And yeah, sure, they may start going towards one another, but what are they going to do? Keep combining until they create the universe? Because that's what essentially the universe is a coordinate singularity. It's a very low density coordinate singularity, but there are high density regions of the universe. I'm getting off track here. Let's get back to this graphic. On the right-hand side, there's a red line to indicate that that's the horizon. I've also got an extended white line beside it. This is to represent the location of the emission of Hawking radiation. And this is an important part that I don't quite understand. It happens at 2 Planck lengths from the horizon. I think that's because there's probably 2 horizons at all locations. And it's not really 2, it's just that you have to have a certain degree of freedom. And that 1 Planck length is the minimum length. And so that's why you have to have 2 for the emission of Hawking radiation, because there's Hawking radiation coming out on all degrees of freedom. And so there's that. There may also be you have to have room for the observer. I'm not quite sure. I'm not a quantum field theory is absurd. General relativity is kind of easy. Quantum field theory gets crazy. And so, I need someone else's opinion on this, but regardless, it's still an amazing thing here. Now, so what I'm saying is, let me just explain what Hawking radiation is. I don't know what it is. I don't think anybody can explain this. It's just something that quantum field theory predicts because of a certain coordinate system. If you have a certain coordinate system, then you have a high enough gravitational energy, it can come from the Unruh effect too, which is just from acceleration. But there's this, from the observer's perspective, there's this thermal radiation that happens because of the geometry of wherever they're located. And this radiation, we know the temperature of it, and it's typically associated with black holes. And so you can say that a black hole it emits a certain temperature of radiation. For Hawking, I had a beer. Anyways, so a black hole has a certain temperature of Hawking radiation that you can calculate depending on the amount of mass that the black hole has. Now, the temperature of the Hawking radiation decreases. It's inversely proportional to the mass of the black hole. So the higher the mass is, the lower the temperature. And so this would seem unfortunate for a model such as mine, because I would not be able to produce Hawking radiation, or I would not be able to match the CMB temperature, which is 2.725 or something like that Kelvin, because that's a fairly high temperature. And if the universe is a quote unquote black hole that's emitting Hawking radiation, then why is it so cold? Because it's for the total mass of the universe, it's something like 1.4, I think, times 10 to the negative 30 Kelvin is the temperature of the radiation that's emitted. It's extremely cold. So to match the C and B temperature, I have to have a very high redshift. Well, at 2 Planck lengths from the predicted horizon, I have a high enough redshift to produce the 2.725 Kelvin. And to me, this is so remarkable because there's a very narrow range of parameters that will allow this. And so I've got a calculator on my website, The Universe is Not Expanding, if you want to explore it there. I would also encourage you to try to replicate it, like dig through this and try to replicate it, because if you get intimate with the equations, you'll be convinced. I mean, I'm totally convinced. When I discovered that at 2, you can make it 1 Planck length and adjust the Hubble constant, you can, but that throws your coupling constant off a little bit. And there's some fine tuning to be done, but you want a horizon that produces the C and B temperature with a uniform Hubble constant. That's kind of the whole idea, and that's where I've arrived at this K equals 0.833. It may be that it, is K equals 0.8, but I don't know. It's just me. But what's amazing about this is, okay, so I can reproduce the Hubble constant. I can reproduce the C and B temperature. For BAO, baryonic acoustic oscillations, that's this thing. It took me like 2 weeks to figure out what it was. And then it took me like 4 hours to figure out why. And so, and I'm still a little confused by it. It's pretty abstract. It's what BAO is. They describe it as this sound horizon coming from the early universe, but it's what it is empirically. So they take the separation distance of all galaxies. And this is not galaxy pairs. That's what confused me, is I thought they were finding galaxy pairs. No, that's not what they're doing. They they have a list of 1 billion galaxies, and then they measure the distance between all of those galaxies. Each one, like all combinations. And there is a small statistical bump for the separation distance of around 147 megaparsecs. They call this a sound horizon from the early universe. Well, talking with ChatGPT, and I know these AIs, man, they'll say anything. But I've spent weeks on this subject studying it, and it has convinced me that it's because if you take the Tolman temperature for this radiation, it's basically the same setup as this Hawking radiation we just discussed. And for that distance of 147 megaparsecs using my coupling constant K, the Tolman temperature drops below the recombination threshold. Now, I'm not sure if that means that mass is being created or not, but it does imply that there is a scale preference. And that preference manifests from the Tolman temperature. Like I say, it drops below that threshold only for that 147 megaparsecs. There's no other distance that it does drop below that threshold. As far as I can tell, that's the explanation. Who in the hell knows? This stuff is so complicated. I don't even know what that means. It sounds to me like the Hawking radiation is being converted into mass energy. That's what it sounds to me like. I'm not entirely sure, though. I think that's enough of chatter tonight. Thank you so much for listening. I don't know what to do next. I just make the same video over and over and just try to improve it. I could write articles and submit to journals. I've tried. They just reject immediately. You email people and they ignore you. I just have to wait, I guess. There's no outlet for this sort of thing. YouTube is the best thing I got, and I'm entirely dependent upon some big influencer listening to this and paying attention and wanting to have a chat and then it going from there. But I'm totally willing to have a debate. If anybody disagrees, I'll debate all day long. I doubt anybody would be up for that. Our culture's a mess right now. The internet's being destroyed by artificial intelligence. It's just being dismantled and replaced with garbage that nobody understands. It's basically chiseling all the garbage that bloggers made over the last 20 years into, it's just chiseling over the bedrock of human knowledge with blogger garbage written by bots. Whatever. Y'all have a great night.